Hello and welcome back to CodeBlaze. I'm back with another Voxel tutorial for Unreal Engine 5. We'll start by going over some issues from GitHub and general refactoring. Then we'll add some color to our chunk using Vertex Colors. Finally, something that has been requested a lot, we'll be tackling adding and removing voxels from our chunks at runtime. We'll be doing that today for blocky based chunks like the greedy meshing one and the naive meshing. And in the end, I'll talk about some performance considerations regarding runtime manipulation of voxels. So let's get started. So we got two issues in our GitHub's repository, and a special thanks to jmancoder and Sharax8 for providing those issues. So basically, first issue was with the UVs, as some of the faces, the UVs were rotated by 90 degrees. And I had the same issue in my Unity implementation also, which I fixed there, and I'll be fixing here when we get by adding textures to our chunks. The second issue was with the 2D height map generation, as I was not considering the chunk world position. So the fix for that is also merged. So you can go ahead and look it up in the repo what all changes were made. So again, I want to thank everyone who's contributing to the project either by raising issues or creating MRs, and you can also feel free to do so, and maybe we'll talk about that in some upcoming video. Apart from the fixes, I have done some more refactoring. Basically, I moved all of the settings to the chunk world object, so there is one place from where I can control it all, and I no need to open the blueprints again and again to modify things like noise map settings and all. So that's generally a good thing. Usually our world object should control the world generation settings anyway. So for that also the changes were made. Again, you can follow them up on the GitHub. I'll link down the actual pull requests that do those changes down below in the description. So adding vertex color is pretty simple. All we need to do is add one more container or mesh data array that represents the vertex color for each vertex. And wherever we are generating our actual mesh data, or basically where we are populating it, we just need to add the generation logic for vertex color. And finally, all we need to do is pass this vertex color to the create mesh function, as it accepts the vertex color parameter. So with this, all of our code side changes are done. Now to actually display the vertex colors, we need a special material. Basically, we need a custom material that will take the vertex color and put it into the base color channel of our material. So it's pretty simple, just like what I'm showing right now. You can go ahead and create this material and make sure your chunks use this material. And with this done, if you run the game, you'll see the colors, whatever you have assigned, appearing on your chunks. Now with just vertex colors and color based voxel generation, you can go pretty wild. You can have set up logics for, depending upon height values, generate different colors. Like for some, you can have grass color as green and some gray color for stones and all. So even with the color based generation, I think you can get some good results. But later on, we'll be tackling how to add textures to these chunks. So onwards to runtime modification. I added a simple crosshair just to know from where we are shooting our line cast rays. Now the idea here is to modify the blocks array and regenerate the mesh. And the complexity lies in identifying which is the correct index in the block array that we need to modify. So basically all we need to do is convert the line trace hit location to the correct block index. The actual line cast logic and the player input is something that we'll handle in blueprints, as I don't want to add unnecessary complexity to C++. This also presents us with an opportunity to start exposing some of our voxel functionality to blueprints. And I think it works nice in a broader narrative also. So the way we'll have it as, we'll have a voxel system with which we'll expose some APIs to blueprints, so that you can easily interact with it. And in general, you gain the most when you work with both C++ and blueprints when working with Unreal Engine. So let's get started. So we'll start by creating a blueprint function library in C++. that will basically have all our, position transformation methods. I'll just search the blueprint function library as a base class. I'll call it Voxel function library. And we'll store it in our utils folder. Okay. So while this generates, well, basically I'm going to skip it, but I did some folder restructuring also. That was again part of my refactoring. So you can go ahead and look at the repository to see the updated folder restructures. Because earlier I had everything in the private folder. Now there are subfolders inside it for better organization. So let's skip while this code generates. So our voxel function library will have just 3 methods for now. First would be the world to block position, right? And next we'll need world to local block position. And finally, world to chunk position, right? So do note all of these functions have been marked as U function. That way they will be exposed to the blueprints and they are of type blueprint pure since they won't be modifying any state, right? And the world to local block position and chunk position actually require the chunk size also, as that would be required in the computation. So let's get started with its implementation. I'll just generate the definitions here. Definitions for all of them. Right, I missed a semicolon here. Okay, so we'll start with the implementation of world to block position first. Implementing the world to block position is pretty simple, right? All we need to do is convert the vector position to an int vector and divide it by the unreal units. We'll just do a f int vector, pass in the position and divide it by 100. Next, we'll implement the world to chunk position. So for this, we'll store the result and finally we'll return the result. And also we'll compute the division factor, which is nothing but size into the unreal scale units. We'll do const int factor equal to size to 100. And we'll also convert the position to an int vector. So we'll call this int position. And this would be f int vector of position. So the actual conversion to the chunk coordinates is nothing but the division of each component of position, or basically the int position, by the factor. So suppose the chunk size is 32, so the factor would be 3200, and in your int position the x component is 200. So when we are in the world where your x is around 200, you actually belong to the chunk 000, basically the chunk in which x component is 0. So to do that, we basically divide position.x by the factor and we get 0. And that's all well and good. But the problem comes when we do this in the negative components. So suppose instead of 200, we are at minus 200. Now in this case, our chunk position would be minus 32, right? But if we divide minus 200 by 3200 and cast it to int, we would be getting 0. So whenever any of our component is in the negative region, we need to subtract by 1 to get around the casting to int normalization. So what this looks like is a bunch of if statements that I'll just copy here, where we check if any of the component of the int position is negative. In that case, we perform the division and subtract by 1. Else, we just perform the division. With this, our world to chunk position is implemented. And finally, the world to local block position in a nutshell is just a difference of the two. So to do this, we'll first get the chunk position. So we'll do const auto chunk position and we'll save it by calling world to chunk position. We'll pass in the position and the size. Next, we'll get subtract this from world to block position. So we can just directly store it as a result. So a result would be world to block position. We pass in the position and subtract by chunk position. Now our chunk positions is going to be in a chunk coordinate system. So it would be 0, 0, 0, then it would be 0, 1, 0. Essentially, it won't be same as what our block positions work in. So we need to multiply this by size, right? Since there will be a gap between the chunks also. Now, you may think we can directly return the result, but there is another point of normalization that needs to happen. Again, it's in the cases if any of the coordinate is negative. I'll just copy over this normalization. Now, why this is needed is something that I'll explain when we implement the player blueprint, as it will be more clear then, because we will do some computation in the player blueprint also. So for now, just let it be here and we can return the result. Right. So with this, our blueprint function library is basically implemented, and we can get started with the actual chunk base API. So in our chunk base, we will be adding a U function. So let's start with view function, and this would be blueprint callable. It won't be pure since we'll basically be modifying state here. And the category, I'll give it as chunk. Right. And this function will actually do both addition and deletion, since we'll be taking the block type also as an input. So I'll just call it what modify voxel, void modify voxel, and the first parameter would be a position at which we want to modify. So const int vector f int vector position, and next we'll take in the block to which we want to modify it to. Const p block. So in case of delete, we would be passing an air block, and in case of addition, we would be passing some other block. Now, to make your blocks exposed to blueprints, you need to annotate your enum with the uenum macro and pass it the blueprint type as a parameter. So this way, your enums would be exposed to blueprints. And along with this modify voxel, we will need another pure virtual function, which would be implemented by your child classes that would actually modify the voxel data. So we'll call this virtual void modify voxel data. And to this, again, we would be passing your position and your block type. So it would be const f int vector position and your e block type e, and we'll mark it as pure virtual. So pure virtual a chunk base modify voxel data. I'm not getting that here. Just copy it. So each of your child classes, basically the greedy chunk and the knife chunk, would be implementing them. And for those two, it would be pretty simple. We just need to modify the blocks array. But for matching chunk, it's a bit complicated. And that is something that I'll show in some later video. Otherwise, this one would be pretty long. So let's get started with the implementation of modify voxel in chunk base. So the modify voxel flow is pretty simple. First, we need to do a bounds check that our position is actually valid and not something outside the chunk size. And next we can call the modify voxel data. So this again would be implemented by the child classes with position and block, right? Next, we need to generate the mesh. Now, before generating the mesh, we need to clear the existing mesh data. So for that, I have this clear mesh method, which basically sets the vertex count to 0. It calls the clear method on the chunk mesh data structure, which is just emptying the T arrays. Now, if you don't clear it, it will try to override the existing data and you'll get some weird results. So make sure you clear the mesh before generating the new one. So we clear the mesh, then we call the existing generate mesh, and finally the existing apply mesh. And that basically comprises of our modify voxel flow. So all we need to do is actually implement these methods in our base classes or the child classes. So we'll start with your greedy chunk here. Right, and I'll create an override here. So alt insert, overriding members, search for modify voxel data. Okay, and for this we'll create a definition. Right, I'll move it down. I want the create chord to stay with the actual mesh generation logic. And it's pretty simple, right? We already have the get block index and we have a position here. So we can just get our index here, const int index. That would be our get block index, take in position dot x, position dot y, position dot z. So our position itself would be transformed in the blueprint itself, and by the time we reach here we have the correct block position, so we can directly get the block index, and then we can take the blocks array and set the index to the block we want, and that again is passed by the parameter, right? And with this, we basically have a modify voxel data done for greedy chunk. We'll quickly implement it for the naive chunk also. Alt insert, overriding members, voxel data, alt insert, definitions, and I'll just copy over the implementation from here since it's same. Right, and so we basically have our C++ part done. All we need to do is now implement the blueprint logic in the player blueprint. So let's get on with that. So now we can start implementing our line trace. So I just opened my player blueprint and I have two events, the right mouse button and the left one. So we'll implement the destroying first. Anyway, the logic is going to be same with the slight change. So whenever this is pressed, we need to do a line trace by channel. And okay, I have one thing. So to get our line traces working, we need collisions on our chunks, right? Because it uses the underlying physics system to do the line trace. And to create collisions, all you need to do is set the create collision flag to true in your create mesh section. So make sure this is true, otherwise your line traces won't detect the chunk. Okay, so we have our line trace here, and I have also created a variable called block distance. This is basically the maximum distance of how long we want our traces to happen. So the default value is 500, I think. Again, this needs to be in Unreal units. So we'll get, for the start point, we'll basically use the camera position. And since our crosshair is literally in the center, and so our camera position is going to be pretty much the same. So we don't need any screen space conversions. So we'll get the player camera manager. get player camera manager. From this we'll get the position, get camera location, that will pass it to the start, and the endpoint will basically be the whatever in this direction, wherever the camera is facing, in that direction, if we multiply by the block distance, that is what the endpoint needs to be. So we'll get the rotation of the camera, get camera rotation. From the rotation we'll get the forward vector, get forward vector. We'll multiply this by our block distance, and we'll need to add this to our camera location because we want relative location from the starting point. So we'll add this here, and this will basically be our endpoint. So let's tidy this up a bit. Yeah, so that's our line trace happening. So we'll do a debug also so that we can see it, and I'll set it to 10 seconds. It's more visible. Okay, then we can do a branch here. So we only need to do if there is a return value. We'll break our result. So we'll break this. And for now, we'll just print the location. So I'll just print string. What do we have here? This location. Right, and I'll increase the duration also. So let's just try it out. Okay, I go here. I was far away. You see the red line here. So if I do this, you see there's a red box here. That means I have hit the chunk, right? And I'm getting the location also printed. With this, we have a raycast logic, and I'll basically extract this to a function. All this, right? I'll right click, collapse to function. We'll call it raycast. Right. So we'll be able to use this raycast function again in our addition also. We actually open the raycast function, make sure it's all tidy. And I'll just change this order here. That way it's more cleaner in the event graph. Right. So we have a raycast done. All we need to do is now do the transformation and modify the blocks. So with our raycast done, we can now actually start using our modify voxel function to actually change the values that we want. So we'll take this hit actor and cast it to chunk base only if there is a hit. So we'll use the branch here. And here is where we'll do another adjustment or normalization, because whenever you do your raycast, and it will hit one of the face of the block, right, out of the 6, and whichever face it hits from whichever direction, so the direction here matters, on that direction the value of the component of the hit location would be some kind of value like 3200 or multiple of chunk size, not chunk size, basically multiple of 100. So it will be a value that if you round down or truncate, it would stay as it is. Now that would be an issue, because if I'm hitting from the negative direction and the chunk and the value I get is as 100, I actually need the block that is before that, right? But we would get a block that is afterwards, because the round down of the value of 100 would be nothing. It would be the same as it is. So to get around this, what we can do is subtract the normal of the hit from the location. That way a value of 100 would become 99, and when we round down 99, it will come out as 0, and that way we'll get a correct location every time. Now again, there is an issue when there are negative components. because it will, in those cases, it will reduce twice, right? So in that case, we will need to adjust it, and that is why we have this second normalization here. So if you actually want to see why this is happening, you can print all of these location values and the world transforms that we'll do, and then you'll be able to see why we need these transformations, right? So let's just get it done with first. Okay, so we'll subtract the location by normal, and we'll take this and call world to local block position. And for this, we need the chunk size. So we'll create a new variable here, chunk size. And ideally, this chunk size variable should be set by the chunk world. But for now, let's just hard code it. In between videos, I'll refactor this out. So we have the block position now. So what we can do is take the chunk base and call modify voxel. We have the position, and we'll set the block type to air. So with this, our modifying voxels should work. So let's just compile and try. Or the engine will crash. Knowing the history of this series, nothing has ever worked the first time. But let's see. So if I go close, since our max block distance is only 500, and I try, yeah. So we are able to remove the blocks. Now at this point, if you start printing out these vector values like this one or after the normalization, you'll exactly be able to see what these are doing and why they are needed. And I think that is something that you'll need to figure out on yourself. Figure out as in understand on your own, right? If I try to explain that, it will get convoluted here. But these things are required, and only by seeing them why they are required, you'll be able to understand it, right? So we have our deletion flow done. Now we'll start with our addition of blocks. So for that, we'll just copy this up because it's pretty much the same. Whenever the right mouse button is clicked, we do a raycast. But instead of directly modifying the block position, we need to find the block position adjacent to the block, right? What I mean by that is, so if I go here and I right click this block, I need to add the block to the position that is here. So basically adjacent to that face. And to find out that, we need to find out the direction from which we are hitting. But that is something we already have. That is our normal value. So what we need to do is, after our block position has been transformed, we just need to add the normal value again. So we'll take this and do an addition with our normal value. Right. And we need to pass it here by truncating it. So this way we'll get a position that is adjacent to the face at which we are hitting. So if we compile it and change this to stone, not air, again compile it and save it. Let's run it, and we should be able to add blocks now. Right. So we can add blocks and delete them. And well, that's basically it for this tutorial. So we have complete capabilities of runtime modification. But there are some caveats here that I'm going to talk about now. So the problem with the current things, and there are actually multiple problems. First of all, I'm not happy with the normalization logic that we are doing. It is a bit complicated, and it's complicated to explain also, right? So I'll keep on trying to come up with a simpler solution. Or if you can find a simpler solution, please do leave a pull request. I'd be happy to include it, right? The other issue is with adding blocks. So if we keep adding blocks, we'll hit a chunk edge. Luckily, we hit it right here. So as you can see, I'm not able to add blocks here. And the reason is because the block right next to this block would be in a separate chunk. but we are nowhere handling that case where our actual hit chunk and the block and the chunk in which we need to add the block would be different. And to handle such case, we need to maintain a dictionary of chunks so that we will be able to dynamically query which chunk we need. And that is something that comes when you start implementing a proper voxel system. So we'll talk about that later in a future video. But for now, do note that is one caveat here. The rest of the issues are with performance, right? Like currently, I was surprised that this was working without any lags, but there are absolutely frame drops happening here also. So to get around that, there are two things you can do. First would be multi-threading, so that our actual mesh generation logic doesn't block the game. So we compute the mesh generation on a separate thread. So that is basically more of a, we are basically offloading the work. The other optimization you can do is do the smart work, right? Rather than maintaining one mesh for the whole chunk, you can maintain the chunk mesh in separate sections, right? So what we have here in apply mesh is basically we are creating one section. So if you divide your chunk mesh in suppose 8 sections and maintain 8 different meshes, then you need to rebuild only a part of the section. That way it will be a bit faster, right? But the issue with that is dividing greedy meshing algorithm in multiple sections is a bit tricky thing because you would have faces that are crossing the section. So the simplest thing would do is you break the faces at section intersections. Wow, section intersections, that's pretty weird thing to say, but I think you get what I'm trying to say is right. Since you can't have faces crossing over in sections. So but you can actually start with the knife chunk, right? So knife chunk is pretty easy to divide in multiple sections. So these are the two performance optimizations that we can do, right? And well, yeah, that's it for today. That's what all I wanted to share. But there's a few things I wanted to talk about. So there is one thing I want to discuss, that was the format of these videos. Like currently, I'm trying to write code along with you and basically record me writing code also. But as we get more into some advanced topics, the video's length may grow too long. Even now, I think this video would be around 20-30 minutes. I don't know. I haven't finished editing yet. But the thing is, what would you prefer? Like, if I directly show you the code and explain it, or do you want me to see write the code line by line? Right. Whatever you prefer, we could do that. So leave that down below in the comments. And for the next episode, there are two things we could do. One would be adding textures, or other would be adding baked ambient occlusion in a greedy meshing. So both of them are viable options. So whichever you would like to see first, leave them down below in the comments. And that's it. Thanks for watching. Goodbye.